How are you? Enzo DiCostanzo, clinical professor of economics and finance, St. Peter's University, Jersey City, New Jersey. Part 2 for the regression correlation chapter, the Excel models. And again, this all feeds into your assignment. I didn't specifically do assignment number 6 problems yet, but you have the models, you have how to do them, all set up. So let's get to that and pick up where we left off yesterday. Okay, folks, we were here yesterday. The regression in the mean. So we stopped here, and we have the bigger problem to work on, and we're going to do that next. Okay, so yeah, regression to the mean is there's a new student and joins the class, and then this is the GPA example. Student's grade point average 3.9, 2 standard deviations above the mean GPA. Would that change your guess? Student grade point average 3.9, 2 deviations above. So the correlation is near 0. Doesn't tell you anything, and it doesn't move your guess. Yeah, this is where, again, how far away from the mean are you? That kind of a thing. Yeah, it says, suppose you're told the new male student was about to join the class, or you have to guess his height in inches. So what would you guess? I mean, the height of the male students. That's suppose you're told that the student's GPA. Yeah, so what they do is you're trying to guess the guy's height, and they give you the GPA. So you're saying from the GPA, can you guess how tall the guy is? I guess the premise being that, tall people do better in school, or that type of thing. Now, if the correlation is 0, that should tip you off that the height and GPA aren't going to tell you anything about each other if the correlation is 0. So that's really the whole theme of what this all is. So, yeah, R can't be bigger than 1. So the predicted Y tends to be close to the mean. Then the corresponding X was a property of the linear line. It's called the regression to the mean. This is why the line is called the regression line. So yeah. So, it's, just drawing that straight line through the snowstorm of points is supposed to be as close to the mean as possible. Okay, that's really, this whole discussion about heights and guessing the GPA from the height or guessing the height from the GPA, that's really what all of that is. Okay, checking the model. And again, we've already done this. Quantitative data conditions satisfied type thing, so it's quantitative variables. We've all checked the linearity condition, checked the independence assumption, and so a lot of this stuff we've gone through. But in the model already, you saw, and we executed this. The predicted, actually, the data minus the predicted is the residual. So we computed a column of residuals. We've already seen that, so we looked at that already. And there's some other stuff in here. It says perhaps most well used model and all statistics, two easily estimated parameters, meaningful measure of how well the model fits the data. Model is useful when the specific conditions are true. The assumptions are hard, often impossible to check. So yeah, quantitative data, not use categorical data, that type thing. Don't use zip codes or credit card numbers in linear models. Linearity condition to describe the is designed to do precisely that and satisfy the scatter plot looks reasonably straight. So if it's not, like Trump keeps some of the V-shaped recovery that we may be looking at. So linearity condition relatively straight, with an angle or a slope. It doesn't have to be horizontal or vertical, but basically scatter plot straight enough type thing. Okay. Outlier condition, points need special attention. Maybe compute them. And we did a couple examples of that where you pulled out 2 points and we recomputed the model and we got a better correlation. And we've sort of illustrated that with a couple examples. Independence assumption. Discussion. Yeah, independence assumption means regression. Residual for evidence of patterns, clumping. Yeah, so the failure of the independence. Of a time series common violations for errors to be correlated with each other. Autocorrelation, the error the error our model makes today, maybe some someone it made yesterday. So yeah, okay. So what at the end of, and going back to the probability chapter, which actually is the next chapter in the chronology of the book, but we've already covered that in when the course started, which feels like a very long time ago, right? The independence assumption is that the points don't influence each other. That's really what it has to be. And when you get clustering and it's say clumping or trends, it says failure of independence, meaning that they're too close together or there's too much influence among the points type thing with one another. And that's something that's a violation of the independence assumption. Plot the residuals, look for patterns. And now, and also in the next example that we work on, we're actually going to plot the residual, the residuals versus the predicted y, and I'll show you how to do that. Right, explore and describe the relationship. Independence is essential. And yeah, and look, as we go deeper in, we're mostly not going to hit chapter 16 in this particular course. And my outline of the material is really going to be 4 to 10, so 4, 5, 6, 7. You know, those 7 chapters are going to be the core going forward. I'm almost done with them. I have to go back to chapter 4, which I know pretty well, and I want to work on chapter 10 at some point, probably in the fall. But over the summer, I'm teaching a corporate finance course. I got to spend the time on that material, so this is going to get pushed away just a little bit, but very important. Like I said, it's a fine career, you know, working, knowing this material that I taught. And this I just gave you a little bit. You know, if you guys know the textbook and know your math well, it'll be a very good career for you guys doing stuff like this. But yeah, we've done this already. It says ScatterPlot of the residuals versus the X value should be plot without patterns. Now it says versus X value, but it's really versus the predicted Y. If you see nonlinear outliers or clusters in the residuals, find out what the regression model missed. There shouldn't be any bends to it. No, it says shouldn't have any. Yeah, so yeah, the residual graph or the residual illustration. As no bends, it shouldn't have any outliers, no direction, no shape, and we'll show you that when we show you that example that's coming next. Standard deviation of the residuals is also something you want to be able to compute equal square condition. And if you're looking at this saying, hey, wait a second, it's divided by n minus 2, and it has this. Actually, this should be here, and it's the square. The summation of just e without the mean. Well, the mean is 0. Which is the whole point of what we did here. So it's just e minus 0 is just simply e, or e minus 0 squared is just simply e squared, which is what we have here. So this is the standard, and as we just said, this is the standard deviation of the residuals. And actually, I should probably have that bolded out. Pardon me, folks. This should be moved. A little, it's good when you have your your master file sort of nearby, so you can, as you're going through it, again, always it's like Picasso or Da Vinci, always adding to it, always adding to it. So that's the same. Now you're divided by n minus 2 instead of 1 because there's more degrees of freedom. Okay, there's a slope and an intercept, which is really why we're doing that. Slope and right, both of those looks like a pattern, and you subtract more. You're subtracting more degrees of freedom is what you're doing with this. Okay. More parameter for each, yeah, because you have a slope and an intercept. Okay. That's why it's divided by n minus 2. R squared and how to compute R squared. And actually this is, so it says a correlation of 0.8. the R squared is 64%. So it means 64% of variation of the model is accounted for in the model. A variation in the data is accounted for in the model. So, and yeah, obviously, if you're if correlation is 0.8 or 0.4 and you start squaring things, you have 4 times the strength or a quarter of the variability one way or another. So that's just some of the math that happens in here. Correlation is 1, the sales are perfectly. I'm sorry, the sales are predicted perfectly. The residuals are 0. There's no variation. So correlation is equal to 1. And you can't do any better than that. The residual from would be just the observed minus the mean. And again, we just said that in the previous section. They have same variability as the original data. Subtracting the mean doesn't change the spread. Okay, compare the sales and variable residuals from the regression. The means have been subtracted to make it easier to compare the spreads. Okay. And this, yeah, so in here, and again, we go back to the Lowe's example. It says, is a correlation of 0.8 twice as strong as a correlation of 0.4? Not if you think in terms of R squared. The correlation means that R squared is 64% and correlation 0.4 is 16%. So it's a quarter of as much as the correlation that's 0.8. So the correlation of 0.8 is an R squared 4 times strong. Okay. So how well does the regression model do? Yeah, so we have something in the textbook. Do I have the textbook? Actually, pardon me, folks. This is the accounting book. I was getting ready for the summer class now, so I'm sort of focused on that a bit. Well, yeah, be patient for a couple seconds here so we get this chapter opened up. So what are we looking for here? We're looking for 6, 7. That says box plots. Yeah, it says compare the variability of sales, the variability of the residuals from the regression. They've been subtracted to make it easier to compare the spreads. The variation left is unaccounted for by the model, but it's less than the variation in the original data. So, yeah, so the residual box plot is a little more compacted. The sales one with the mean subtract is a little more spread out. Okay, so it means you have a little bit of, so that's the point of these models, is to sort of tighten up your estimate relative to the points of the data. So that makes, something, those pictures make sense compared to, relative to what it is that we're talking about in this particular chapter. Folds them between the two extremes, 0 correlation, perfect correlation, okay. So regression model with correlation -0.5 is doing as well as one with positive 0.5, different directions. Now you square a lot of this. So now we're looking at the you're squaring the correlation. So you look at the Lowe's model, and it's 0.9. The correlation was 0.976. You square, so it goes from about 97.6% to 95.2%. So 4.8% of the variability has been left out of the residuals. That's how you interpret that. Okay, so it's 1 minus the 95.2%. That's R squared. So mean is R squared 0 means none of the variation in the data is in the model. Okay, so there's no correlation, okay, which is what that is, which is certainly, you need a different model, you need something else. Then it's how big should it be? You compare it to other models in the realm that you're working in. Is the regression reasonable? Statistics are based on data. When you perform the regression, does it make sense? And don't just, and here, I love this quote here, I should put this in big font. Don't trust computer output only. Don't trust that stuff. Okay, you've got to understand what's going on. And this last piece here, nonlinear relationships between the variables. You obviously, this particular chapter, it's got to be linear, but a lot of them are going to be nonlinear. And then the relationships among the variables. And then what you have to do is you have to find models that are going to help you model that. Okay, and that's what you need to do. Okay, yesterday we stopped here, I think. Yeah, we stopped at the cyclist getting hit by the car or something like that. Yeah, we worked on this yesterday. But now we're going to work on the cyclist data. I initially gave you the data. We started with this, and then we're going to make this graph, the residual graph. The model's going to be a little bit longer. Okay, so we're going to be looking at that next. And actually, what we're going to do, let's get to where that is in the the Excel here. So you're here. Yeah. So you're right here with this. You got to start with the data, and we'll just take it from there. Okay. And so you have the whole lecture, at least, with still a few weeks to go in the course. Let's just find the correlation coefficient, interpreting the linear model, examining the residuals, understanding R squared. So we're doing all of this. So we have the data on the cyclist accidents from the previous page, and actually what you have or what you can do, and we'll see if it's going to fit. I think it is 41. And I just want to get the data in. There's 11 pieces of data, I hope. And actually, we can count these, but 08 to 9. Yeah, I think this is it. That's just the data. I'm just copying and pasting it. Okay, we'll put a 1 in here. It's already sort of pre-formatted. Equals this plus 1. Control D. Okay, and then you have the averages that are already. Actually, we had the formulas in there already, so they already. But that's a sum over the count. Okay, so I'm just going to leave that there for a second, so you guys can take a look at it. All right, it's just a sum of the 11 pieces of data over how many. Or you can just divide by 11 too, or reference 11. But I try to make it automated as try to be sophisticated as possible. Actually, this is this. Okay. Put a border around that. Always making it better as we go along. Okay. This is the response. This is the explanatory variable. And actually, you know what we could do even before anything. Let's get this graph up, or get the graph. I think we can make that model. Let's get the graphic up. So, and I'll tell you, for something like this, you can just do this because the X and Y are right next to each other. You're going to say insert, scatter, right there. Yeah, there it is. Okay. Those are 2 pieces of data. Now, I made this is, I clicked the first chart layout with the titles and everything, and let me go to layout and legend, put the legend up top. We've done this many times over the years. Okay, make this thing a little bit. And we'll go through all the steps of how to make your graph look like this. Okay, this bottom, this minimum here, this is mileage. Right? Control A. That's mileage. This is what that is. Okay, this bottom minimum should be 30, and the space, the major unit spaces should be 2. And what are we doing here? Is it mileage? Could that be mean age? Oh, pardon me, mean age. What am I doing? I apologize for that. That should be mean. I don't know what I'm thinking. That's mean. It's got to make sense, folks. Right? Mean age. And these are the years. So this will be a notch smaller. And I think we could get every year in here, not 2 years, get 1 year in. Okay. And yeah, you don't even have to go to angles because we made everything a little bit smaller. Right? We made it 9. The font was 9 instead of 10. And this was year. Okay. So these little markers here, built in, 0, make it go down to 4. Okay, so it's pretty good, right? We're pretty good. And this is the title, so this is mean age cyclists killed. And again, we're looking at this in terms of from a couple years ago, so it stops at 08 or something like that. But don't be concerned about that. Okay, they're pretty good. But now we're gonna clean it up a little bit more. Let's fill this thing with something very light and border it with something very dark. The grid lines. Let's make these grid lines half that one. Just the little dots in there. Okay, and let's give it a shadow. Format, shadow, there we go. That's it. Okay, you have all the years in there. This, oh, actually, we could have done 2. I did 1 year on this. Let's do 2 years. Well, I was going to say make it look a little bit better. 2 years. And space it out a bit. Okay, have a shadow, and then right-click, select the data, edit. I want to put the name in. This is mean age years. Okay, in years. All right, there you go. Here's your scatter. We'll cut it. And see what says graph. Just going to move it over. Okay. There's your graph for this. There's your first one. Okay. There you can go. Get this little bit of room. Like I said, you're going to care more about the borders when you learn how to use the PDF writer and that type of thing. We can't make the other graph yet because we don't have the, and actually, let's make these a little small. We don't have the, I'm saying I have it, but I don't think a lot of you have the PDF writer. Okay, so we'll get to that. We'll get to that. Now, it's just a similar discussion from before. Okay, you're going to come in here, you're going to take a piece of data, you're going to take that X, you're going to subtract out the mean, you're going to anchor that. Okay. And there you go. Okay. There's your deviations. We're going to start with your deviations, which are x minus x bar. I'm just checking 5 minus 5. Okay. And this other one, you can go like this. Right? That's your y. And here, I'm just going to do something terrible. Just grab it like that. There you go. There's those deviations. Minus 5, 3.8. Yeah. And now you're going to square them. All right, and we have underlines here. You're going to underline both of them, and you're going to say equals sum that whole column equals sum that whole column. Okay, and this is the total sum of squares, and then you're going to cross we're going to multiply together the 2 deviations. All right, 99. You have the means there. Yeah, so you have all that. We can't hit the prediction yet because we don't have the standard deviations. You can see that we have the residual here. But here, let's just sort of take a second and just make sure that you're absorbing what happened here. Okay? You good with all that? Okay, the year, the age, time. Okay. Deviations of squares, all that stuff. Next thing we're going to do is start working on the deviations. So this is going to be the square root. And I should even, well, here, you need this. And again, that's just the count. And again, some of these folks, I apologize, some of these were sort of already in here when we were working. This is just the count of all your data. So I type equals count and then put the range in, right? And that's it. This is the square root of the sum of x of the variation squared divided by n minus 1. Right? So equals SQRT, the summations of x divided by parenthesis n minus 1. Okay, so 3.32. Now, we were lucky that we uncovered standard deviation of the sample, and you're just going to highlight all of your x's, and that's it. And you'll get sort of the computer programs version of this, and it's the same number. Okay, sure, it's nice to check using the Excel function, the standard deviation of the sample, but I'd much rather you understand how to make it just by using square roots and dividing. That's it. Okay. This is the Y version. which is there, 3.09. And this is going to be these guys. Oops. Right there. 3.09, those are the same. And we don't have the residual version yet. And again, folks, I sort of have to apologize for this. The slope thing sort of showed up here. Yeah, let's compute correlations next. And the correlation can work in a couple different ways. Where's the formula? Yeah, it's this formula here. I did both sides of this, so let's just do the left-hand side. Top one is the summation of the x and the y bar divided by SQRT, parenthesis, the summation of the x squared times the summation of the y squareds. Okay, so it's all that. Yeah, 0.965. Right, that's it. So there's those three numbers manipulated. Okay, and then the other version of this is the summation of x, the differences in the x and the y, oops, equals, they're just x and y, divided by parenthesis n minus 1 times sx, the standard deviation of x, standard deviation of y. Okay, same number. We just did the math. That's a little more complicated, that version. Okay, but I just use these formulas that are just right here. And these are the slope formulas, and the slope takes the correlation coefficient times the ratio of the deviations, and this is the intercept. Okay, which takes the slope times x bar. Okay, and then what you do is this is the predicted version of this. So you say equals y bar, lock it, and then what are we doing? Plus slope, lock that, times the x. Yeah. So those are all your predicted equations. You're not adding them or anything, but yeah, 41.6. So yeah, so it tells you the mean age for the years, what we predict, and this is the data. This is the set of data, and this is what you're doing. Okay, this is so you do this for some historical numbers, and then you project a couple years forward. So you say, 2009, 2010, 2011. You do a little bit of a prediction with all this. Okay, which is really what happens. Okay, so that's your y hat. The residual is the difference. This is your E column, which we just very briefly lectured on that today. So equals data minus the predicted column. Here's all your residuals. And the mean of these things, we found the average is just 0. You could type an average and then put the range in, or do sum by count like I did. Okay, and then this other piece here, this is just the square that we're going to be using in a computation. Now, again, why does it give me 15 decimal places? I do not know. When I need 2, and it fights me to enter 2. There we go. Underline. And this is the sum of something. This is the sum of the squared residuals and some of the squared errors. Okay. So equals sum of those 11 squares. Okay, so we've made our scatter plot. Now the deviation of this is simply going to be of the E, of the residuals. And that's divided by n minus 1, but we're going to do it divided by n minus 2 is how we're going to do this. So this is going to be, what are we doing here? This is the square root of the sum of the residuals, and this is 11. And this is, I think, minus 2, though. Yeah. Okay. Yeah, the square root of the ratio of the sum of the differences in the residual squared divided by n minus 1. You have the number, actually n minus 2 for 2 degrees of freedom because there's a slope and an intercept. So, and again, I didn't see I'm sure I'll learn eventually how to do the standard deviation with the second degree of freedom. So, and actually what we can do, just very quickly while we're here, go to help. We'll type in standard deviation 2 degrees of freedom. This is the standard deviation function. Yeah, I don't see, because now once you get sort of, yeah, see, this it's by n minus 1. Okay, so this is how Excel does it. Okay, this is their standard deviation. So we want n minus 2, and this is an example of that, type thing. So there's a lot of help in the Excel. If you just hit the help button, there's a lot of help in this. Okay, we'll leave that there for later. Okay, so what do we do here? We did equals either one of these r's squared. This equals this. This equals 1 minus that. And this is equal 1 minus SSE, the sum of the errors, divided by the sum totals here. There, sum total of the squares. Right, it's the same thing, 93.17%. Okay. So that means 93% of the variation is explained in the model, and only about 7% is in the residuals, which is pretty good. Okay, and then you have the equation here, and the intercept, the slope. It's all sort of typed out for you guys. And actually, did I do the concatenation version up here? I didn't do it for you. Oh, yeah, I did. Yeah, I did it right there. Okay. Copy. So we're going to do, this is y hat. And what are we doing here with this stuff? This is, yeah, so this is AD 180 is what I want. And then I want AD 179, I hope. Yeah, I want another decimal place out of this. Oh, this is AD. And this thing needs a comma in there too. So yeah, this needs a little bit of work. So yeah, so let's go to this, and let's go to text. And yeah, I want a comma. Yeah, there it is. I put 2 zeros in. Okay, so this is the y hat using the concatenation function that we worked on yesterday. And see how this goes? Okay, open this up a little bit. Okay, so it's yeah, it's obviously a lot more working, folks. I mentioned this the other day. You know, a couple decades ago, you used to have to be able to work like this. Believe it or not, in the word processors, you had to go to that level. So what you guys have is very nice. This was normal doing something like this to type things out in numbers and make computations. That's how you did it. You had to know a lot. It wasn't the user. Obviously, what's the advantage to Apple and all these companies? If it's easy to use, everybody's going to use it. If you have to be a computer scientist to use a cell phone, not a lot of people are going to use it. Okay, so, but that's how that works. Okay, and again, after all this math, we're going to conclude. It says the mean age cycle has increased by about 9/10 of a year during the decade. So yeah, that's what that means. So the age increases by about a year. Your people about a year older on average from 10 years ago. Change in age over the change in years. How does the plotted values show how the plotted values were calculated? What does the plot suggest about the model? Okay. The predicted values of the mean age found for each year by substituting the value into the linear model. We did that already. Okay, we interpreted the variation in the model. Okay, about 93% is accounted for in the equation, and 7% in the residuals. And the other thing that we can do that we didn't do across the board, we'll do it right now. We want the residuals graphed. So let's get over there and do that. So here, we did a lot of work with this graph and formatting. So let's just sort of drop it in there again. Okay. And we're going to look at residuals and predicted age. So what was this? So this vertical one. This is residual. This is predicted age from the equation. Okay. Predicted mean age. Yeah, so this is, let's give another line to this, and this is going to be residuals for linear model. Okay, and this stuff is a little bit smaller. Then you right click, select the data you're going to add. The X is what's predicted. And the Y are the residuals. And what do we call that stuff? Yeah, we just called it residuals. Oh, here, yeah. And the other piece of this, right click, select the data, remove that, hit OK. And now down here, you have to go back to averages or automatic, right, for everything. And then we'll see where everything is. You know, auto, right? Yeah. And then now we can sort of fix this up a little bit. Right click, to test the squares. So built-in circle for, okay, and I think the lowest thing is 30. And yeah, that's pretty good. Just like that. Okay, those are the residuals. Now again, let's sort of compare. Yeah, pretty good. Yeah, here's a scatter. It's just, so let's just bring this up up a bit so you guys know what that is. And here, we don't need 2 decimal places here. We just need 1. Okay, and options fixed to is 1. Okay, something like that. Yeah, I guess you could mess with it a little bit, put these things at an angle, make them a bit smaller. Okay, but there you go. Okay, so there's the remainder of this, the in-class notes and chapters in here. Let's see what yeah, there's some other stuff down here I don't think we talked about. So you made the equation, it answered a bunch of questions, and then it says, you know, the semiconductor companies, quarterly stock price, they have a correlation of 0.86. Before drawing conclusions, what would you like to see? You want to know if the scores are quantitative, linear condition, outlier condition are satisfied. If coworkers track the price in euros of these companies or dollars, you're going to have the same variations. That's not going to change correlation. Standardizing would change you know, your analysis of it, that's for sure, because you're making a constant change in both in the prices from dollars to euros. There's an association, but you can't, you know, the prices might vary, but don't say, oh, because how one semiconductor company does versus another, they're all going to go into it. There's an association, but you can't say it's causal. Okay, to be very you know, statistically oriented. Yeah, positive correlation means they're both low or both high together. You know, that's what that means. How strong is strong, weak, moderate, and strong. Least correlation is as a measure of association. Doesn't have units, treats X and Y symmetrically. There's a whole set of rules here. Correlation coefficient gives the direction of the association. Okay, there's some tables, and I worked that up. But I suspect that I'll be you know, working on some you know, I suspect I'll be working on some more examples for this and the normal distribution chapter. Folks, there's still a few weeks left in the course here. Let's look at the calendar here. Right, this week, next week. Okay, so I said the 10th. I wanted everything in by the 10th. So we're here on the 28th. So you have this week, and so you have a good 10 days and a few more. You still have 2 weeks, the 10th, the 11th, even if needed to be. But like I said, I told you guys we were going to be working on something, you know, the rest of the way here. Yeah, I hope you didn't wait with normal distribution and the quantitative data, and now you can spend a good 6, 7, 8 days on this. Okay, and like I said, let's look at the template very quickly here. Where's the template? Here's 6 for the template. Yeah, it's the same, all the same stuff. Okay, I may do the number. You know, we'll do another video probably. We'll do all the number 2. So that'll be the next. Probably not tomorrow, but it'll be soon. It'll probably be the end, you know, Thursday maybe. The disk drive example. And I'll go through all this and we'll discuss, and you know, 20 and all these other kinds of things, the price on capacity, and there's some other examples here. But I'll definitely do another video for you guys. So please, you know, don't be concerned about that. But like I said, folks, you know, spend the time on this. You know, learn all the things that they had to learn. So you guys will be responsible for the bookstore. But I'll do the disk drive one soon, so you guys have an example of that. Okay, and go to Blackboard, folks, and yeah, I'm going to update that. This is the assignment template. So if you go to the, again, you have to go to the bottom of these things and look at all the tabs here. You know, it's going to be here. So you go to the regression correlation tab, which is down at the bottom here, and you know, you arrow up and arrow down. You guys know from class, you know, we have these things go deep into the, you know, into the files. Okay, so you got to spend the time. You got to spend the time, folks. I hope you had a good year. Like I said, I'll have at least one more video coming for you guys. But you know, the country will be back to normal. You know, within a year we'll be back to normal. So you got to be thinking about jobs and working. So don't just think this is just a vacation. I think I said that in the initial emails. This is not just a, you know, you guys having a break from a, you know, from working. Okay, you have to, you know, you had to keep working hard. I hope that's what you did. Yeah, there it is. Yeah, so folks, I hope you worked hard, you know, these last few weeks, and you took advantage. You know, it's going to be worth it. Please learn this material. I keep saying it over and over again. Okay. All right, folks, we'll see you next time. And like I said, go to Blackboard. The assignment template's going to be posted up there. All the assignments have been there for a while, and like I said, spend the next couple days working at everything. Okay.